Number 14, and this is about Collatz sequences. And actually, there's a YouTuber who you might have heard of called Veritasium, he's a little bit better at making videos than I am, and he has a really, really good video on this that I think you should watch instead of this one, to be honest. But I'm still going to make this video. um, so we can define the Collatz sequence as if n is even, then the next term is n over 2, and if n is odd, then the next term is 3n plus 1. And then they give an example starting at 13 of how it sort of converges to 1 in the end, and notes that there are 10 terms. Now, it's not been proved yet because it's really, really quite difficult, that any starting number will end at 1, but for now we're going to do something slightly easier, which is for starting numbers under 1 million, which starting number is going to produce the longest chain. And this note, which sends shivers down my spine, says that the terms are allowed to go above 1 million. And my interpretation of this is going to be, not only can they go above 1 million, but they can go above, the biggest integer possible in Scala. Therefore, rather than using normal ints, probably a good idea to use big ints for this problem. Cool. And this is a fairly straightforward statement, I think, to translate into code. So yeah, let's give it a go. So I've just copied that sort of arrowy version of it like that, and let's see if we can translate this into code. So we want to get the chain length of a big int for the reason I was sort of saying before, that I'm afraid that the numbers are going to start getting too big and we're going to get into some sort of overflow. I think the way to do this is with a tail recursive function. We want to keep track of the chain length as we're going, so this is something we'll be adding 1 to, and I think it's probably okay to have it as an int. And then we want the number that we're deciding, what do we want to do with this number, and that's a big int. And we're going to define this, and it's going to return the chain length, so it's going to return an int. Remember, for recursive functions, you're going to want to specify the return type, and then we're going to call it starting with a chain length of 0 and n, which is the number we're interested in, and this function itself will of course return as an int. The question then is, what do we do in this function? And I think what we can probably do is we can probably just do a case match on x. So let's see, so if x is 1, then we need a fat arrow. If x is 1, then we're done. We've bottomed out, and we can just return the chain length that we've already got to. And I think, is the chain length of 0 correct for 1? That might be enough by 1, but what I'll do is I'll run it and see what happens. And then I guess I'm running out of letters now because I'm using x there, so maybe let's call this y. And then we can say if y is even, and the way to tell if something is even, of course, is when I divide it, when I take the remainder dividing by 2 is do we get 0? And if we do, then the instructions are telling us that we need to run this sort of function again. We need to add 1 to the chain length, obviously, and then we just need to put in n over 2, like that. And then the case match, if it's not even, then it's odd. So we're going to need to do, we still add 1 to the chain length, and instead we do, well, it says n there, so that's a silly mistake there, so that should obviously be y. That would obviously break if I actually did it. So maybe I should actually pull out this go function somewhere else so it has a different scope so I can't get confused. We'll maybe do that later to sort of precify the code. And then that's what we want to do if n is odd. And I think that should be it. So if we comment that out, just format the code. I think I had stuff highlighted when I pressed format then. And if I just try and get the Collatz chain length of, was it 13 in the question? Yeah, it was 13. Let's see what it spits out. So I think it'll be enough by one error, realistically. So it contains 10 terms, and here we're getting 9. So I think we want to say that 1 has a chain length of 1. So we want to start it with 1, like that. And it says this is an unreachable case. That's interesting. Is it because it needs to be a big int? I suspect it's because... But then I don't understand why that works at all, actually. That's really interesting, actually. What's this saying? So we can have the tail recursion annotation so that we get the checks. Big int cannot be used as an extractor. Okay, well, I think it works, but let's just check that this case actually gets hit. It might be just me misunderstanding Scala, to be honest. But let's see. So let's check this actually gets hit by just logging hello and running our function. So it does get hit. I think IntelliJ is just a bit wrong, which is fair enough. Like there's probably some sort of weird boxing/unboxing going on or something like that. But the point is this works and it gives us the correct result for 13. Okay, so let's remember what the question actually was, which is which starting number under 1 million produces the longest chain. Okay, so we just need an iterator of numbers. So if we do iterator dot from... No, let's do dot range, actually. Range it from, I guess, 1 to 1 million. And if we use 1 million, that's like everything is strictly less than 1 million. And it says under 1 million, so strictly less than is what we want. We're going to need to map these guys to big ints to use our function, I guess. And then we're going to want to... Oh, gosh. We are going to want to max it by this function here, like that. And that should give us the answer. Eventually. So it took 1 second, which is kind of fine for Project Euler. Like 1 second is kind of fine. I think the official rules are like it should really take less than a minute. So let's see if that's right. It is. Great. So that's the problem solved. So we could potentially try and think of some optimizations. I mean, 1 second is perfectly fine, as I say, but we can probably do a bit better. So I think one optimization, and I think it's even mentioned in Veritasium's video on it actually, is that in the case where we've got an odd number, we know that 3 times an odd number is always going to be an odd number. We know that adding 1 to an odd number gives you an odd number. Therefore, we know the next number is an even number. Therefore, you can kind of compress the step of it being odd into just a single step. So I think if we did this, and instead we added 2 to the chain length, I think that should give us the same answer. And it might be a bit faster because you're doing fewer recursive calls, but I don't really see why it would be, to be honest. I mean, it's the same sort of stuff going on. And I mean, if we run this a couple of times, like there's nothing in it. It's just not. It doesn't matter. It really doesn't matter. So that's like a micro optimization that no one cares about. I think the other thing that actually might help is if we memoized lists, because we know that I guess, for example, if we go back to the problem, I know that if I am at, say, 26, obviously that's immediately going to take me to 13. But I already know what the answer for 13 is because I've already done it. So you could potentially just remember all of the answers, and that should, in theory, speed things up. The only problem is that you end up sort of maintaining a map of previous answers that you search for each time that's going to end up having a million entries in it, right? So with memorization, you've always got to think about, like, well, is the cache of stuff that I'm remembering getting too big, and then it's actually taking too long to even find the fields that I'm looking for. So I could try that, I guess, but I'm quite satisfied with this answer right now. So I guess I'll leave it as an exercise to the viewer, and maybe I'll make a sort of follow-up video on this. But yeah. But yeah, I think that's it from me. Thank you for watching, and I will see you next time.